Welcome! Geothermal energy is a clean source of energy derived from the heat naturally stored in the earth. Geothermal energy has been known for a very long time, and more than 2,000 years ago, Chinese, Greek, and Romans, and many others were enjoying thermal baths and hot springs. Hot water was also of great importance for medical purposes, and since more than 150 years as a source of chemical components for industry. Since the beginning of the last century, very hot waters from geothermal systems are used to produce electricity. Very special conditions are needed, which we'll look at in a later stage. In the last decades, geothermal energy is increasingly used also for heating. This trend will continue because waters for heating do not need to be extremely hot, and therefore well-suited settings are common. All in all, geothermal energy is considered one of the key components of the energy cocktail which will support our societies in the next future. Think at Iceland, where only transport uses fossil sources. This is what a valid geothermal system looks like. In principle, it's easy. We need some heat, a good reservoir along which water can flow, and the fluid itself. Note that the water recharge and discharge can be fully natural or driven by humans. Good predictions of the three components of the system are obviously key for the scientific, technical, and eventually economic success of the project. The first component we look at is heat. One fundamental source of heat derives from the fact that the Earth is cooling, which results in heat being transferred from the central parts of the planet to its surface. For the time scales we're interested in, we can assume a steady state. The resulting planet-scale geothermal gradient is shown in the plot. You can see that temperatures in the most of the mantle, from the core mantle boundary to the base of the lithosphere, are fairly constant. This is due to the vertical movements of mantle rocks driven by mantle convection. The portion of the mantle experiencing significant convection ends at the lithosphere-asthenosphere boundary, which we know it is an horizon characterized by temperatures constant of about 1300 degrees. Assuming that the asthenosphere is an isotherm surface, that the Earth's surface is also roughly at constant temperatures, that all the rocks between have the same material properties, then temperature changes between the two surfaces will follow a linear trend. The lithosphere, however, is not composed only of mantle rocks, but also of the crust. And the crust has a lot of granites, or, more in general, rocks with a high portion of radioactive minerals. The resulting geotherm, therefore, predicts higher temperatures. A typical average gradient in the crust will be between 20 and 30 degrees per kilometer. From a thermal point of view, the lithosphere is then defined by the two isotherm surfaces, the LAB and the surface of the Earth. Considering the heat equation and making the necessary assumptions of thermal properties, we can establish a link between the lithospheric thickness and the heat flow Q, which can be measured at the surface of the Earth. We conclude that heat flow is a proxy for thermal gradient and therefore for the depth of the lithosphere-asthenosphere boundary. Assuming representative values, you obtain that the average represented heat flow in normal conditions is about 60 milliwatts per square meter. This can be used as a reference to identify warmer than normal regions and colder than normal regions. The map of heat flow in the picture shows patterns which are correlated with the tectonic features we have known before. The hottest places are clear the mid-oceanic ridges, where new oceanic crust is being created. Fairly hot are also subduction zones, such as those around the Pacific. Looking in more detail, you can see warm regions in Western Europe and along the East African Rift. The regional thermal field discussed above is at places affected by local disturbances which dramatically increase the geothermal potential of the region. The most important of these are magmatic intrusions, Considering the melting temperature of magma of around 800 degrees, and assuming that it is in place at 10 kilometers depth, you can predict a gradient of 80 degrees per kilometer. And one of the most famous geothermal fields, that of Larderello in central Italy, the geothermal gradient above the Pluton is even more than 100 degrees per kilometer. Combining this geological information, we can predict areas potentially interesting for geothermal energy. Rifts. Here, the lithosphere-asthenosphere boundary is shallower than the surrounding as a result of extension tectonics. In addition, rifts are often associated with volcanism and magmatism. This is particularly the case for Iceland, where the mid-oceanic ridge is exposed with its intensive volcanism. Subduction zone, where high temperature are present just on top of the subduction zone and is associated with intensive magmatism. Typical places are New Zealand and Japan. Once you have the heat and the right temperatures, you obviously need a reservoir which is permeable enough to contain the water and to let it flow. Primary porosity is commonly present, but is often not sufficient to guarantee enough flow. Fracture porosity is of great importance in geothermal systems, especially those at high temperature, as you will see in the next clip. Note that the most important characteristic of fracture is the aperture, which among others depends on the orientation of the fracture with respect to the stress field. We have now reached the last component of the geothermal system, namely fluids. These can have two different origins and therefore compositions. In sites where magmatism is important, there are abundant fluids generated by the degassing of the magma body. These fluids are hot, loaded with very special minerals, and chemically very aggressive. When they reach the surface, they form fumaroles or even geysers. On the other side, precipitations can enter the system from the surface of the Earth and migrate downward until they are heated enough and start moving up again. Mixed water patterns are common in high-temperature geothermal systems. Your role as a geologist is a very important one. Similarly to what mentioned in previous clips, the core of your mission will be to develop a hydrogeological model as correct as possible, inclusive of geometries, physical properties, and their uncertainties. The better you model, the more efficient and sustainable will be water management.